somebody has their mic on. But yes, I'm actually doing it at USF right now. So, but yeah, so let me know if you guys have any questions. But I did post the notes, so I have the basal ganglia notes online as well as the cerebellum notes. I put a lot of work into those notes because I know the lecture was quite complex, so I put a lot of time into those notes. So hopefully, it's beneficial and really helps you study throughout the weekend because I know those 2 lectures were really difficult. So yeah, so I definitely put a lot of time into those notes. I also finished writing the practice exam. So the practice exam's done. I'm just gonna tweak probably a few things here and there, but I'm gonna post it today. So the practice exam will be up today. So that's done. But yeah, I've been working on that these past couple of days throughout the week. So again, if you guys need anything doesn't have to be neuro, any life, etc., whatever, just let me know, right? So yeah, so feel free to download the lecture. It's under neuroscience block 3. It's going to be basal ganglia as well as the cerebellum. Yeah, I've been in super overdrive. I was working like 12 hours yesterday, like all day on this stuff. But yeah, it's because I know how confusing these lectures were, and when I got them last year, I was kind of just memorizing things just to memorize. And I think if we really understand the topic, it's going to be much easier for us for the exam, specifically basal ganglia as well as the cerebellum, because there's so many pathways. So yeah, well, you'll see when we get to the notes and stuff like that. Okay. Lots of coffee yesterday for sure. Okay, so I'm going to share my screen. Okay, so I'm hoping everybody downloaded the notes. I'll give you a few more seconds, so just in case anybody came in a little late and wants to download the notes. But does anybody have any questions before we start? Okay. All right, so we're going to talk about the basal ganglia, and then we'll talk about the pathways. You'll see I put a lot of pictures in here as well for us to really get a good grasp of what the basal ganglia is for. And we'll just get right to it, right? Okay, so basal ganglia, it's basically a bunch of structures that are combined into one, basically. So it's a bunch of separate structures in the brain that they classify as the basal ganglia, right? And basically, the basal ganglia is really important for regulating movement, right? But specifically, it's going to regulate the upper motor neurons, right? So it's kind of like, I want to do this movement, but the basal ganglia is going to be like, okay, let me adjust the upper motor neurons, and eventually the upper motor neurons send a signal down to the lower motor neurons and cerebellum to say, okay, this is the movement we want to do. So basically, the basal ganglia is kind of like that, executive function in regards to movement when we're talking about the upper motor neurons, right? So we'll talk about some subcortical loops as well as the indirect and the direct pathway and how they play a really important role in facilitating or inhibiting movement depending on which pathway. Right, so you can see here, so here's the basal ganglia, right? So it's a bunch of different structures, as we can see. So here in this picture on the left, so you can see a bunch of different structures are going to form the basal ganglia. So the ones included in this bullet point right here, the globus pallidus, substantia nigra, et cetera, et cetera. We'll talk about those a lot in detail when we talk about the pathways. But again, the basal ganglia only connects to the upper motor neurons, right? So it's only regulating upper motor neurons. It doesn't connect to the lower motor neurons and the lower circuits that actually move the arms and the body. It's kind of just like the cerebellum. The cerebellum is only going to regulate the upper motor neurons, which we'll talk about that in the next lecture. But the basal ganglia, again, is just going to be important for the smoothness of our movement, right? Stopping and going and being able to be really smooth with our movements, right? So that's going to be the main importance of the basal ganglia. One thing to note is that when we talk about the striatum, that's the same thing as saying the caudate or the putamen, right? They're basically the same structure. The only place where they're separated is going to be when it's divided by the internal capsule anteriorly. Remember that internal capsule is that white matter tract that has all the axons, right? All the axons sending down to the lower body. Anteriorly, we have that, and that actually separates the striatum to the caudate and then the putamen. So again, if you see people saying striatum, caudate, putamen, it's basically all the same thing. And I'll talk about that in the upcoming slides. Okay, so again, so we have the striatum, right? So basically that contains our caudate and our putamen, right? And those are going to receive inputs from the from the cerebral cortex, right? So it's kind of like the first thing our cerebral cortex is saying, okay, I want to initiate this movement. It goes down to the basal ganglia, and basal ganglia is like, okay, what do we need to do to make this happen, right? So that's kind of like what the basal ganglia is for. So we have these neurons that are actually called medium spiny neurons in the basal ganglia, right? And they're actually just neurons that look like, spines. So that's why they call them medium spiny neurons, right? So they're all located throughout the basal ganglia. A lot of them are located within the striatum, as you can see right here. Remember, again, the striatum is that caudate and that putamen, right? So caudate and putamen are basically going to be that striatum. And we'll talk about the globus pallidus. Okay, so these MSNs, right? So again, quick recap, we have our basal ganglia, right? It's important for just, smooth movements, right? So starting and stopping movement. And we have our striatum, right? Again, that's our putamen and our caudate, right? And it's going to have basically two types of MSNs, right? Which are medium spiny projections. They both release GABA, right? So what does that tell us? That tells us, okay, well, we know if both the MSNs release GABA, and then the MSNs are located mostly in the striatum, that means the striatum is going to be inhibitory, which is true, right? The striatum is inhibitory. So the striatum, which contains the caudate and the putamen, are going to be inhibitory. And we'll talk about that when we talk about the pathways. So you can see that D1, right? So we have D1 MSNs and D2 MSNs. D1 MSNs are going to be activated by dopamine, right? So when you have high levels of dopamine, D1 is activated, which activates our direct pathway. We'll talk a lot about this. Don't worry. If it sounds confusing, don't worry. We're going to pound this into the ground when we talk about the direct pathway. But again, remember those D1 neurons are going to be for the direct pathway. Then we have our D2, which is going to be inhibiting movement, right? That's our indirect pathway, which inhibits movement, right? So we're going to have D1 versus D2. And we'll talk about the outputs of the basal ganglia in great detail when we talk about the direct and indirect pathways. Okay, so the basal ganglia, so we talked a lot about, remember, the basal ganglia is a bunch of structures that are within each other, the globus pallidus, the subthalamic nuclei, the striatum, right? All these structures make up what is called the basal ganglia, right? And we know it's important for motor functions, right? We'll talk about later at the end of the lecture that the basal ganglia is also important for non-motor functions, right? But we'll talk about that at the end. So two of the loops that he mentioned is the motor loop as well as the ocular motor loop, right? So we see our motor loop, and this is basically saying, okay, I want to make a movement, right? Your cerebral cortex tells you I want to make a movement, etc. Sends it down to the premotor, somatosensory. Then it goes into the striatum. If you remember what we said, remember we have, the striatum releases GABA, so it's inhibitory, right? So we activated the putamen or the striatum, which is inhibitory. This will inhibit the globus pallidus internus. The globus pallidus internus will not be able to inhibit the thalamus, and then that will then activate the premotor cortex. I know that sounds like a lot. Don't worry, we're going to break that down in regards to what is inhibiting what and what is going to be exciting what to understand this pathway. But the big overview is basically we have excitatory and inhibitory functions depending on which structure you're talking about in order to perfectly modulate the movement, right? Because think about it, if we just excited everything, we wouldn't be able to have, smooth movements. We have excitation, inhibition in order to calculate that perfect movement, right? So that's the same thing over here with the ocular motor loop in order to help with eye movements, right? So ocular motor we know is very important for eye movements. All right, so we have the direct pathway. So again, remember, recap, we have our basal ganglia, right? It's just a bunch of structures put together. Our subthalamic nuclei, globus pallidus, our substantia nigra, striatum, right? All these structures make up the basal ganglia, right? We have two types of MSNs. We have D1 and D2. D1 is going to be excited by dopamine, and that's going to be the direct pathway, which we'll talk about right now. D2 is going to be excited by low levels of dopamine. So that'll be the indirect pathway, which will inhibit movement, right? So again, here we have a good basis already, and we're ready to tackle this direct pathway. So direct pathway is going to facilitate your movement, basically allow you to obviously move your your extremities, etc. Okay, so you'll see that I added basically a lot of pictures per slide because I feel like the best way to learn this information is to actually see it in images. So you'll see I added a lot of images throughout the PowerPoint, and we'll be going through them step by step in order to really understand the process of what the basal ganglia does. Right, so again, here's our direct pathway. Right, so our direct pathway, remember, that has the D1 MSNs. Right, those are excited by dopamine. Right, so you can see we have excitation via the cortex as well as excitation via the substantia nigra pars compacta, right? So the substantia nigra pars compacta makes dopamine, right? And you can see this is going to activate the D1 neurons in the striatum. So that's the first step, right? The first step is saying, okay, I want to make a movement. Our cortex tells our basal ganglia, which is excitatory, as well as our substantia nigra, sending to our striatum saying, okay, we have high levels of dopamine. We want to initiate a movement. Okay, so the D1 neurons, the D1 MSNs in the striatum are now activated, right? So the putamen and the caudate are now activated. You can see that in this image. You can see the cortex right here, right? It's exciting the putamen as well as the caudate, right? These two together make up the striatum, okay? These two make up the striatum. So after that, we're thinking, okay, what happens when we activate the striatum, right? If you remember the striatum has the MSNs that release GABA, right? So the striatum is inhibitory. So you'll see on the next step that the striatum actually inhibits the next structure, right? So here you can see the striatum actually inhibits the globus pallidus internus as well as the substantia nigra pars compacta. So you can see right here, okay, from our first image, we saw, okay, the cortex, send excitatory signals to the striatum, right? The caudate and the putamen. Then the caudate and the putamen, also known as the striatum, became excited. But remember, the striatum is inhibitory. So when the striatum is excited, it is going to inhibit the following structures to come, which is going to be the globus pallidus internus and the substantia nigra pars reticulata. So you can see right here, the globus pallidus internus is going to be inhibited, as well as the substantia nigra pars reticulata is going to be inhibited. Right, so again, quick recap, remember, so I'm telling myself I need to make a movement. The cortex sends a signal to my striatum saying, okay, we want to send an excitatory signal to the striatum because we want to initiate a movement. Okay, the substantia nigra, which produces dopamine, produces high levels of dopamine, which sends it to the striatum to say, okay, we need to initiate a movement. So now the striatum is getting two excitatory signals, and the striatum, now that it's activated, what does it do? Right, the striatum, remember, is inhibitory. So it is going to inhibit the globus pallidus internus as well as the substantia nigra pars reticulata. Right, okay, so that's the first part of the pathway. And what's next? So you're going to think, okay, the globus pallidus internus is inhibited, right? So we're thinking, okay, so what is the globus pallidus internus supposed to do, right? What is it going to do to the next structure? And we can see that the globus pallidus internus and the substantia nigra pars compacta actually are supposed to inhibit the thalamus. But you're probably thinking, oh, we just inhibited the globus pallidus internus. So what is that going to do to this pathway? Well, that'd be a great question, right? Because what's going to happen is that since the striatum inhibited the globus pallidus internus, right, and the substantia nigra pars reticulata, they will not be able to inhibit the thalamus, right? Because the function of the globus pallidus internus is to inhibit. If that inhibitor is inhibited, it will not be able to stop the thalamus, right? Do you guys understand that, right? So basically what's going to happen is the thalamus is now going to be excited, right? The thalamus is now going to be disinhibited. This is disinhibition, right? What disinhibition is basically when you stop the inhibitor from inhibiting something, right? So we stop the globus pallidus internus from inhibiting the thalamus. So now the thalamus can send an excitatory signal to the cortex and initiate the movement, right? So thalamus goes to the cortex and initiates the movement. That is the direct pathway. So again, quick recap because I know it's a lot of information. Again, so it's basically I want to make a movement, right? So I want to make a movement. The cortex is going to send a signal to the striatum, which is glutamate excitatory, to say, okay, we want to make a movement. We're also going to get information from the substantia nigra pars compacta, right, which produces dopamine. It's going to be high levels of dopamine, right? Because high levels of dopamine activate the D1 MSNs, right? So D1 MSNs located in the striatum. So now we know, okay, the striatum is now activated, right? The striatum is inhibitory. So since the striatum is activated, it is going to now inhibit the globus pallidus internus and the substantia nigra pars reticulata. Typically, the globus pallidus internus and the substantia nigra pars reticulata are supposed to inhibit the thalamus, right? But because the globus pallidus internus is being inhibited, it will not be able to inhibit the thalamus, right? So thus the thalamus is now disinhibited, right? That is disinhibition. So now the thalamus is now excited because it doesn't have all this internal globus pallidus like stopping them. The internal globus pallidus is like, you're free basically, you can go, right? Go right ahead. So then the thalamus gets excited and sends a signal to the cortex and leads to facilitating of movement. Right? So which of the following structures in the direct pathway directly inhibits the internal segment of the globus pallidus? Anybody have any questions while we wait? Okay, the answers are looking really good. That's great. Okay, so again, so which of the following structures in the direct pathway directly inhibits the internal segment of the globus pallidus or the globus pallidus internus? Right, so again, remember the first thing that happens is that the cerebral cortex and the substantia nigra pars compacta both activate the striatum, right? So the striatum is inhibitory. The striatum basically is going to inhibit the globus pallidus internus as well as the substantia nigra pars reticulata. And remember, the striatum consists of the caudate and the putamen. So then, thus, C is going to be the answer, caudate, right? So again, caudate and putamen are both going to be together called the striatum. Right, so really good job with that. I know it's a lot of information, but I really hope that the images are really, putting this pathway into your head and making a lot of sense of it. Okay. So again, so here's the direct pathway, right? This is just the chart that he had in this lecture. So this is exactly what we talked about, right? We saw it in like actual images, right? We saw the cerebral cortex and the substantia nigra pars compacta activate the striatum, right? So high levels of dopamine activate the D1 MSNs. Right? We just talked about that, right? High levels of dopamine activate D1. The caudate and putamen, which is part of the striatum, are going to inhibit the globus pallidus internus. Typically, the globus pallidus internus inhibits the thalamus, right? But since the striatum is actually inhibiting the globus pallidus internus, it will not be able to inhibit the thalamus anymore, thus leading to activation of the thalamus and excitatory signals to the frontal cortex, right? So the thalamus is disinhibited. You can see that here. Disinhibition of the ventral anterior and ventral lateral thalamus makes inputs to the cortex more effective, right? And that's exactly what we talked about, right? This is basically what we talked about in the images, just in a single chart, right? But I feel like seeing the actual pictures and seeing the structures makes it a lot easier to comprehend. Yep, and then these D1 MSNs facilitate movement. Okay, any questions on the direct pathway? Okay, so, all right, so the indirect pathway is a little more complex, right? So we'll get into it. Let me know if you want me to slow down, right? But I want to make sure we really understand this, right? So again, quick recap, right? Basal ganglia, we have all these structures, right? The striatum, which is the putamen and the caudate. We also have, we'll talk about the subthalamic nuclei, the globus pallidus, the substantia nigra pars compacta. All these structures make up the basal ganglia, right? The basal ganglia is going to regulate upper motor neurons, right? Not the lower ones, right? So upper motor neurons, right? So that's the basal ganglia. And again, remember at direct pathway, the D1 MSNs, so D1 medium spiny neurons, are going to be activated, right? Those are going to be activated because they're activated by high levels of dopamine that will flow through the entire direct pathway and eventually lead to activation of the cortex, right? So that's going to facilitate movement. Yeah, he didn't respond, or he didn't say which receptor, but typically it's probably going to be an AMPA receptor. It might be an NMDA, but it most likely would be an AMPA receptor. But it can be NMDA. Okay, so we have indirect pathway. So this is going to inhibit movement. First things first, right? So we have, okay, we want to inhibit movement. This time we are not trying to facilitate a movement, right? We want to inhibit this pathway. So the first thing that's happening is, okay, what is going to be different, right? The cortex, is still going to send an excitatory signal to the striatum, right? Okay, so striatum is going to be activated, right? But again, remember that the striatum is inhibitory, right? The striatum is inhibitory, right? So over here we have the substantia nigra pars compacta. Because this is the indirect pathway, and we want to inhibit movement, we are going to have low levels of dopamine, not high, right? So it's going to be low levels of dopamine. So low levels of dopamine activate which MSNs? D2, right? It's going to activate D2 MSNs. And if we remember, the D2 MSNs activate the indirect pathway. The D1 MSNs will not be activated, so the direct pathway will not be activated, right? So again, we have low dopamine activating the D2 MSNs in the striatum. So the striatum is going to be excited, right? It's going to be activated. So here it is right here, cortex coming in, activating the caudate nucleus as well as the putamen, right? So what's the next thing that happens? The striatum is inhibitory. Again, right? Striatum is inhibitory. So the striatum is actually going to, remember this time, it's the external globus pallidus. It's not the internal. This is going to be the external globus pallidus, right? So you can see it right here. Do you see this image, exciting the striatum, and eventually it's going to inhibit the external globus pallidus. We talked about the internal globus pallidus in the last one. So again, it's going to inhibit the globus pallidus externus. Okay, so now we're thinking, okay, we had low dopamine levels, we activated the D2 MSNs, we activated the striatum inhibited the globus pallidus externus, right? So what is going to happen next? What does the globus pallidus externus do? So here, this is going to be a little more complex, but stay with me. So basically, the striatum is going to inhibit the globus pallidus externus, right? That's the first thing, right? So we know, okay, striatum is going to inhibit the globus pallidus externus. If you follow this arrow first right here, the globus pallidus externus inhibits two structures. One of them is the internal globus pallidus. And if we remember the internal globus pallidus was part of our direct pathway, right? So over here, basically, the striatum inhibits the globus pallidus externus. If the globus pallidus externus typically inhibits the globus pallidus internus, it will not be able to do this anymore because the striatum inhibited the external globus pallidus. Are you following, right? So since the globus pallidus externus is inhibited, it will not be able to inhibit the globus pallidus internus. And if you remember from the previous slide, if the globus pallidus internus is not inhibited, right? It's not inhibited, right? It's going to lead to inhibition of the thalamus, and then the thalamus is not going to be able to send signals to the cortex, thus leading to inhibition of movement, right? So again, quick recap, remember the cortex sends an excitatory signal to the striatum. We also have low levels of dopamine, which are activating the D2 MSNs, right? So striatum's like, yay, I'm excited, right? So Striatum's excited, but remember, the striatum is going to be inhibitory, right? So when it's activated, it's going to inhibit the globus pallidus externus. The globus pallidus externus typically inhibits the internal globus pallidus, but because the globus pallidus externus, right, is inhibited, it will not be able to inhibit the globus pallidus internus, and thus the globus pallidus internus is like, yay, I get to do what I typically do, which is inhibit, right? So it's going to inhibit the thalamus, and then it's not going to allow for movement, right? So again, if it helps you remember, basically the globus pallidus internus has an I, right? So basically meaning it typically inhibits, right? So if you inhibit an inhibitor, then it's going to be excited, and then vice versa, right? So if that helps you remember what the globus pallidus internus does. No, so yeah, no, good question. So basically, remember that the D2 MSNs are excited by low levels of dopamine, right? So when the substantia nigra pars compacta is sending low levels of dopamine to the striatum, our D2 neurons are having a party basically because they love low levels of dopamine. So they're going to be excited, right? So that means the striatum is going to be excited, right? But specifically the D2 pathway in the striatum, right? So then the cortex is also sending excitatory signals, so that's also allowing for more excitation of the striatum. Does that make sense, Inga? Okay, so we got the what?
So that minus sign by the D2 is just saying that like low levels of dopamine activate it.
Exactly.
Okay, that's very misleading.
It is very misleading. Yeah, it is. That's why I didn't like the chart that much. So that's why I just used this.
Okay, thank you.
Yeah, no problem. Yeah, it's activated by low levels of dopamine. Okay, yeah, make sure you write that down. Okay, cool. So we got this part of the pathway, which is going left. This part right here, so the external globus pallidus, or the globus pallidus externus, that's what I like to call it, typically inhibits the subthalamic nuclei, right? But again, remember, the striatum is inhibitory. So since the striatum is inhibiting the globus pallidus externus, the globus pallidus externus will not be able to inhibit the subthalamic nuclei, right? It can't inhibit it. And what is the purpose of the subthalamic nuclei? So on the next slide, we'll see the subthalamic nuclei is actually excitatory. Right, so you'll see on the next slide, the subthalamic nuclei is excitatory, right? So it's going to excite the globus pallidus internus. So again, recap. So we got to recap this, recap so we can really understand this. Cortex comes in saying, okay, we want it in, cortex and substantia nigra pars compacta, we want to inhibit the movement, right? So again, you have the cortex coming in and the substantia nigra pars compacta, right? So again, this is low levels of dopamine. Low levels of dopamine, D2 MSNs are having a party, right? They love low levels of dopamine. So that means that's going to activate the indirect pathway, right? So the striatum is activated, specifically the indirect pathway, okay? When the striatum is activated, again, we're going to pound this home. The striatum is inhibitory, right? So the striatum is going to inhibit the globus pallidus externus, right? Globus pallidus externus. When the globus pallidus externus is inhibited, it will not be able to inhibit the subthalamic nuclei. So thus, the subthalamic nuclei is free, right? It's free to go, and typically the subthalamic nuclei excites. So now the subthalamic nuclei is going to excite the globus pallidus internus in the substantia nigra pars reticulata. And what does the internal globus pallidus do? The internal globus pallidus inhibits the thalamus. So you can see in this pathway, globus pallidus internus inhibits the thalamus, and it will inhibit movement. So the external globus pallidus. Lots of questions. Hold on. Yeah. So yes, high levels of dopamine will inhibit the D2 neurons, right? Because remember, dopamine, depending on the level, is going to activate different structures, right? So high levels of dopamine, D1 neurons are having a party. They love it. Low levels of dopamine, D2 neurons are having a party. They love it, right? So again, it depends on the level of dopamine. Okay. Yeah, I can run over it again. Yes, exactly. Yeah, exactly, Savannah. Okay, yeah, I can run over it again, of course. Yeah. So again, I know it's a lot. I want to just recap so we really understand this. So again, cortex sends an excitatory signal to the striatum, right? So again, pound into your striatum is inhibitory. Striatum is inhibitory, right? So again, substantia nigra pars compacta sends low levels of dopamine. Low levels of dopamine means D2 neurons are super happy. D2 neurons activate the indirect pathway, right? So, okay, again, we know that the striatum is going to be activated. Striatum is going to, when it's activated, it is going to be inhibitory. So the striatum is going to inhibit the globus pallidus externus, right? So if you inhibit the globus pallidus externus, the globus pallidus externus will not be able to inhibit the subthalamic nuclei. Again, these things that are written right next to them are what these things typically do, right? So the globus pallidus externus typically inhibits the subthalamic nuclei, right? But because the globus pallidus externus is inhibited, it will not be able to inhibit the subthalamic nuclei. So now the subthalamic nuclei is going to be able to do its natural function, which is excite the internal globus pallidus and the substantia nigra pars reticulata, right? So subthalamic nuclei excites the internal globus pallidus, and we think, okay, what does the internal globus pallidus do? If we remember from the previous slides, right here, the internal globus pallidus is going to inhibit the thalamus, right? So the subthalamic nuclei is like, okay, hey, I want to keep exciting the globus pallidus internus. I want to keep exciting, keep exciting. And we know when the globus pallidus internus is excited, it's going to keep inhibiting. So you can see it's going to keep inhibiting the thalamus. Thus, the thalamus will not be able to send a signal to the cortex, and that's going to lead to inhibition, basically, of movement. Um, yes, yes, low levels of dopamine excites D2, and high levels is going to excite D1. Yeah, and then, yes, exactly what you said. Cool. And again, that's the last step, right? The globus pallidus internus right here inhibits the thalamus even more. And thus, the thalamus will not be able to send excitatory signals to the cortex, and thus leads to inhibition of movement. Okay, so again, one last recap. So we have our cortex and the substantia nigra pars compacta sends low levels of dopamine. D2 neurons are having a party. Indirect pathway is going to be activated, right? So striatum is going to be activated. Striatum inhibits the globus pallidus externus. Globus pallidus externus typically inhibits the subthalamic nuclei, but because the globus pallidus externus is inhibited, it will not be able to inhibit the subthalamic nuclei. So now the subthalamic nuclei is like, yes, I am not held back anymore. I can do what I'm born to do, basically. So the subthalamic nuclei is able to excite the globus pallidus internus. Globus pallidus internus typically inhibits the thalamus. So now it's going to inhibit the thalamus even more and then lead to decreases in excitatory signals to the cortex and thus inhibit movement. Okay, yes, I hope it's helping a lot. I know it's a lot. I'm just trying to make sure, it's review, review, review. It's a lot about just going over it over and over again. So do you want to do two? Do you want to do two? Striatum. Yes, 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 yeah. So if you're yes. So when the striatum is activated, it's always going to be inhibitory, regardless if it's direct or indirect pathway. It just depends which neurons you're activating, right? Because if you activate D1 by high levels of dopamine, you're going down that direct pathway. If you activate the D2 neurons by low dopamine, you're going down the indirect pathway and inhibiting movement, right? Cool. Yes, yes, exactly. Okay, so that's that. Okay, so all the following are true regarding the indirect pathway except. Damn, y'all are quick. You must really know your material. It's really good. I got you. Yeah, for sure. I told you I'm working really hard on these notes because I remember last year I got these two lectures and I was like, oh my gosh, what is going on? I was like, I'd never heard of these words in my life. So I didn't want you to be in the same situation I was in last year when I was going through this lecture. Okay, so all the following are true regarding the indirect pathway except, right? So everybody seems to be on page. Um, this is great. So it's going to be D, right? So again, remember, the striatum is going to be activated regardless if you go down the direct or the indirect pathway, right? The subthalamic nuclei is typically going to be activated, or it is going to be activated, because that is going to inhibit the globus pallidus, right? So again, remember that this is going to be D, right? Inhibition of the internal segment of the globus pallidus, because again, if you inhibit the globus pallidus internus, that's going to lead to excitation, right? Which is not what we want. That's going to be down the direct pathway, right? So again, I can show you on this last slide just to show you the last thing. Again, typically we want to excite the globus pallidus internus so that the globus pallidus internus can inhibit the thalamus, right? Because if you excite the globus pallidus internus, you inhibit the thalamus. So again, that's why we do not want to inhibit the globus pallidus internal segment. D. Yeah, so I'll show you on the next slide. Yeah, great question. So yeah, the globus pallidus externus, yes, is typically going to inhibit both the globus pallidus internus as well as the subthalamic nucleus. What type of questions? So I would say, I mean, he can ask you questions on the pathways, right? Understanding the pathways, what activates what, et cetera, et cetera. He can ask you in deficiencies. He can ask you in regards to what type of, pathway does Parkinson's take, what type of pathway does Huntington's take. So he can type. I would say those are the types of questions in regards to the basal ganglia, right? So yeah, again, so this is basically the chart that was on the lecture, right? So we already went over this, which is great, right? So we'll just recap it right here one more time. So again, we have our cerebral cortex and our substantia nigra pars compacta, right? So here we're activating the indirect pathway. So what's happening? Okay, so we have low levels of dopamine. Low levels of dopamine from the substantia nigra pars compacta. The D2 neurons are having a party. So now the D2 MSNs are like, okay, we are going to activate the indirect pathway. D1 is going to be inhibited, right? So you will not go down the D1 pathway. So D2 pathway is activated, right? It's going to inhibit the globus pallidus externus, right? Because again, remember, the striatum is going to be inhibitory. So it's going to inhibit the globus pallidus externus. If you inhibit the globus pallidus externus, the globus pallidus externus will not be able to inhibit the globus pallidus internus, and will not be able to inhibit the subthalamic nuclei. So thus, the subthalamic nuclei is activated. That activates the globus pallidus internus. The globus pallidus internus is not inhibited by the globus pallidus externus, so it leads to even more excitation of the globus pallidus internus. So now the globus pallidus internus is like, damn, like, I'm ready to go. Like, I am like, super excited. Nothing is inhibiting me, basically, literally nothing. So then the globus pallidus internus does what it normally does and leads to inhibition of the thalamus and leads to inhibitory signals to the frontal cortex and thus inhibiting movement, right? The one thing we didn't talk about was right here is that we also get cortical excitation to the subthalamic nuclei, right? So again, and one more thing I would note is that not only does, the globus pallidus externus inhibit the subthalamic nuclei, but we also have the cerebral cortex, which is also activating the subthalamic nuclei, right? So again, that is going to be the indirect pathway in summation. Any questions? Okay, so now we have, so basically dopamine. So again, just another recap. Remember, D1 MSNs love high levels of dopamine. So dopamine high levels are going to enhance D1 activity and facilitate movement. And then low levels of dopamine, we know, are going to activate the D2 MSNs and inhibit movement. So this picture right here is just basically suggesting that, we're always having the indirect pathway and the direct pathway activating, inactivating each other, because what this allows is to, allow us to have smooth movements, right? If you just have excitations the entire time, you'll just be, throwing your arms side to side. If you just have inhibition, you'll just be, static. So, there's always just, just back and forth between this direct and indirect pathway to allow for, true smooth movement, right? And that's exactly what the purpose of this basal ganglia is to allow for really intended, calculated, smooth movements. Okay, so one more thing he talked about is in regards to a salient stimulus. So, let's say like you're studying, right? Let's say you're studying, you have your window next to you, and all you see is like a ginormous bird fly across your window, right? So basically you're like, oh snap, like, like what was that? And you like kind of pause for a second, right? You kind of like freeze for like a split second. Why does that happen, right? And this pathway basically describes that. It describes why we freeze in those moments, basically for a split second, may it be basically in those moments of a salient stimulus, right? So basically what's happening is that the first thing that's going on is the thalamus basically receives this salient stimulus, right? So for example, that bird flying across your window, right? So the bird flies across, you get like shocked for a second, right? So the thalamus sends a cholinergic burst, basically. So a huge amount of acetylcholine to the striatum, right? So what's going to happen there? So basically, when you send these like acetylcholine basically into the striatum, it's going to actually do two things, right? So it's actually going to inhibit the cerebral cortex, right? So it's going to inhibit the activity to the cerebral cortex to the striatum, and it's going to activate the D2 MSNs. And you're probably thinking, how does that happen, right? So basically, acetylcholine, right, in the striatum is going to inhibit the inputs basically from the cerebral cortex to the striatum by inhibiting it presynaptically, right? What actually happens is that acetylcholine comes in and it's like it binds to these M2 receptors, and I don't know if you remember from pharm, but the M2 receptors are typically autoreceptors, so they're actually receptors on the synapse that inhibit on the presynapse that actually inhibit release from your own synapse, right? So they're kind of like a feedback mechanism. So basically, that acetylcholine is actually activating those M2 muscarinic 2 receptors on the inputs from the cerebral cortex. So when that's activated, remember that's the feedback mechanism, right? So that's actually going to inhibit the signals, which is exactly what it does, right? It inhibits the signals from the cerebral cortex to the striatum. So we get that, right? It does it presynaptically because we have these M2 receptors that are going to be activated by that acetylcholine and lead to a feedback that's basically going to say, hey, we have too much acetylcholine. We need to, decrease our firing. And that's exactly what happens here. Right? You have a decrease of firing from the cerebral cortex to the striatum. At the same time, right, acetylcholine is going to activate the D2 MSNs, not the D1 MSNs. And you're probably thinking, why does it activate D2 instead of D1, right? And the reason being is that it activates D2 because we have these receptors on D2, these muscarinic 1 receptors. If you remember from pharm, remember M1, M3, and M5 are excitatory. So M1, basically, when it's activated, basically, it's going to lead to activation of the D2 neurons. And then what's interesting is that the D1 neurons don't have that M1 receptor, right? The D2 neurons only have it. So thus, it will only be able to activate the D2 MSNs, right? So now D2 MSNs are only activated. So now we're thinking, okay, if the D2 MSNs are the only ones that are activated, we're going down the indirect pathway, right? So again, quick recap. I know that was a lot, right? So you're sitting, you're studying, minding your own business, right? And then, you know, a bird across. You freeze for a second. You're thinking, how did that happen, right? So what happens is that the thalamus sends a huge burst of acetylcholine to the striatum, and the striatum says, okay, what do we do with this acetylcholine, right? So this acetylcholine is going to inhibit the input from the cerebral cortex by acting on those M2 autoreceptors, right? So it's going to inhibit that, but it's also going to activate the D2 MSNs because the acetylcholine activates a muscarinic 1 receptor that's only found on D2 MSNs. It is not found on D1. So the acetylcholine will not be able to activate D1. So then acetylcholine activates D2, and then we go down that indirect pathway, right? So now the striatum is activated, leads to inhibition of the globus pallidus externus, right? If the globus pallidus externus is inhibited, it will not be able to inhibit the globus pallidus internus and will not be able to inhibit the subthalamic nuclei, and thus the subthalamic nuclei activates the globus pallidus internus even more. The globus pallidus internus is not inhibited by the globus pallidus externus, and then the globus pallidus internus is going to be able to inhibit the thalamus and then lead to inhibition of movement. Okay, I know that was a lot. Does anybody have any questions regarding that? It's super interesting though, because that's what causes you to freeze for a split second, right? Because you go down that indirect pathway and you freeze for a second, acetylcholine stops, and then, you know, and you go back to normal. Okay, so that's what happens in regards to salient stimulus.
Justin,
Yep.
can you explain the part where the acetylcholine goes into the striatum? What happens to the cerebral cortex again?
Yeah, so this acetylcholine actually activates M2 receptors from presynaptically from the cerebral cortex. So when the cerebral cortex is sending axons down to the striatum, it actually has these receptors on the presynapse that are called M2 receptors, and those acetylcholine activate those M2. And those M2 receptors are actually feedback mechanisms. So when you activate those, it actually inhibits itself, right? Because, you know, we always have feedback modulation. So it inhibits the input from the cerebral cortex. That's why you see red lines here, right? Acetylcholine now, it also activates the D2 MSNs. And we're thinking, how does it activate D2? It activates D2 because we have a muscarinic 1 receptor, a specific one that's on D2 MSNs and not found on D1, right? So since it's found on D2, acetylcholine will activate the D2 MSNs and we will go down the indirect pathway. Does that make sense?
Yes, thank you.
Okay, no problem. Yeah, it's actually really interesting, right? Because, you know, this is what literally causes you to freeze for a split second when you go down that indirect pathway. Okay. Oops. So that's exactly what they're talking about here, right? You get that thalamic burst, right? So the thalamus sends a huge burst of acetylcholine, right? We have a quick pause, and then eventually, basically, you go back to normal, right? So again, you have that quick pause, and then you go down that indirect pathway, right? So this is why the indirect pathway neurons or MSNs, D2 MSNs are very, very prominent, right? This is like, you know, a cat walking and first spots a bird, or when a stranger walks into a saloon, basically in an old Western movie. Okay. And what they found is that, you know, that quick pause basically in acetylcholine, that quick pause, right, in your movement is what causes a quick burst in dopamine, right? So what they found is that, you know, this actually elicits a reward, right? It elicits habits, right? So basically, simultaneously, you know, when the cholinergic interneurons pause in the striatum, it causes a burst in dopamine, right? So that's interesting because, you know, sometimes it's hard to change your reflexes, right? So sometimes, you know, some people do different things when something scares them, right? Some people scream, some people run, some people yell. Those are types of habits, right? Those things are hard to change, right? They're like kind of like instinctual. Like, you know, you always scream when someone scares you or something like that. That's hard to change. And why does that happen, right? It's kind of like this reward pathway, right? Because dopamine leads to habit formation. So that stop of acetylcholine really quickly, or that pause, from that cholinergic neuron, when this happens, actually leads to an increased spike of dopamine, which leads to that habit formation, right? Which makes it so hard for us to change our habits in regards to these like quick reflexes, right? And that's why it says, the most important thing on the slide to know is that dopamine contributes to habit formation, right? So that pause causes an increased release of dopamine and leads to an increase of habit formation. Okay, so here, they just did a few studies. Over here, they basically activated the direct pathway via D1s, and they also activated the indirect pathway, and they wanted to see what would happen, right? So here, the most important thing to note is that, when you activate the direct pathway, we know that's increasing movement, right? You increased your locomotion, you reduced your freezing. That's exactly what we see, right? So from the pre over here, when we activate the D1 MSNs, you can see that ambulation increased, which is this dark red, right? That means our locomotion increased, and what's in white is our freezing. So you can see our freezing decreased because we're activating the direct pathway. The opposite goes for D2, right? When you activate the indirect pathway, you have way more freezing, which makes sense, right? Because you're activating the indirect pathway, you're inhibiting movement, and you have way less locomotion. So that's exactly what's shown here. So Parkinson's disease, right? So we know it's a progressive movement disorder, chronic. Most important thing to note, you want to know TRAP, right? Those are the main motor signs for Parkinson's disease, right? So TRAP, tremor, rigidity, bradykinesia, as well as postural instability, right? And then, two things that he noted in lecture, I just highlighted, was REM sleep, effects in REM sleep, as well as orthostatic hypotension. I think what's in blue, if you note those, you should be good in regards to this slide. Okay, so you have Parkinson's versus non-Parkinson's, and basically what happens in Parkinson's is that the inputs to the striatum are lost. Basically, the dopaminergic neurons, that are in the substantia nigra are basically broken down. They're basically dying, right? So the substantia nigra pars compacta is not able to produce dopamine anymore because the neurons are dying, right? They can't produce dopamine. So you have very, very low levels of dopamine. And what's the first thing that you think about? Like with Parkinson's, right? If we have low levels of dopamine, what pathway are we thinking about? Right? It's the indirect, right? So we're thinking, okay, this most likely will take an indirect path, right? And that's exactly what's happening in Parkinson's disease, right? So in Parkinson's disease, we have these neurons, these neurons in the substantia nigra pars compacta, which produce dopamine, right? They're very important in producing dopamine. They produce a lot of them, right? So when these neurons are dying, right, they don't know why, right? But these neurons if they start to die, you won't be able to produce dopamine. If you can't produce dopamine, we're thinking, the first thing we're thinking in our head is, okay, we have low levels of dopamine going to the striatum. Which neurons are going to be activated? D2 MSNs, right? Because the striatum is still perfectly normal. The striatum is fine. The entire pathway is fine. What's wrong in Parkinson's disease is that the substantia nigra, the dopaminergic neurons are dying, right? So we have continuous low levels of dopamine going to the striatum. So thus, we are leading down the indirect pathway. And if you go down this entire indirect pathway, we know that inhibits movement, right? So with individuals that have Parkinson's disease, it's a hypokinetic disorder. Hypokinetic, less movement, right? Because you're activating the indirect pathway in Parkinson's disease, right? Continuously, you're unable to activate this direct pathway because you're not able to produce enough dopamine, right? So then obviously it's a disorder that they haven't found a cure for because they don't know how to stop these dying neurons, right? They don't know how to stop the dopaminergic neurons from dying in the substantia nigra pars compacta, right? And that's exactly what's happening here, right? They tried to find in a mouse study, right? They tried to destroy the dopaminergic neurons in the substantia nigra, and they tried to see a Parkinson's-like state, right? Because if you kill those neurons, it leads to a Parkinson's-like state, and they found basically that they can actually kind of rescue those neurons basically do this. They can kind of rescue those neurons basically by activating the direct pathway in these mice. But again, these studies are very, very, in their, rudimentary stages in regards to trying to make sure that they can find a cure or treat Parkinson's disease, right? Because when there's low levels of dopamine, right, it's very hard to find ways to increase those levels of dopamine because then what's happening is that neurons start to degenerate, pathways start getting affected, right? So it's a very, very unfortunate disease, but again, it's a hypokinetic disorder. So again, Parkinson's disease, you can see here are some of the drugs. We talked about levodopa before, anticholinergics to help with, the muscle stiffness, right? And as well as antidepressants, right? Those are for, the mental health aspects of Parkinson's disease. I put this slide here, right? But he really didn't talk too much about the genetic disorder. He kind of like, flew through this slide. I don't even think he talked about it. But again, if you do want to note them, they are here. Right? I would just note the names of them, right? That should be suffice. But again, he didn't even talk about it, so I'm not going to spend too much time on it. Most important thing here, he flew through this. Just know that forced exercise can improve motor control. That's it. In Parkinson's disease patients, right? That forced exercise can improve motor control in patients that have Parkinson's disease. That should be suffice in regards to this slide. Okay. All right, so another question. So we have high levels of dopamine will excite which structures and lead to the activation of which pathway? You guys should know this one. Let's see. Give you a few seconds. Give you a few seconds. Okay. Cool. All right, so you guys, we've been hammering this, so this is great. So high levels of dopamine will excite which structures and lead to the activation of which pathway? We know that activates the D1 MSNs and that activates the direct pathway, right? So again, low levels of dopamine would activate the indirect pathway, and again, remember that's with Parkinson's disease, right? The substantia nigra can't produce dopamine; those dopaminergic neurons are dying at a fast rate. So then you constantly have activation of that indirect pathway via D2 MSNs. Okay, here, this entire lecture, we've been talking about the motor functions of the basal ganglia, right? And what it does in motor movement, because we know that the basal ganglia is highly involved in motor movement, right? But it also has some non-motor functions, right? So A was the motor circuit we talked about. B, this is going to be our circuit that's important for executive functions. And in C, this is going to be our limbic, which is important for socially acceptable behavior, right? So again, no need to note all these, do not, note this entire pathway. Just note what's on the upcoming slides. So basically what's right here, we have this dorsolateral, prefrontal, and lateral orbital frontal cortex, which is also called the associative circuit. Just know that this contributes to executive functions, right? So if you know that this pathway is helping with, executive functions, rule inference, working memory, et cetera, that should be suffice, right? I would just know that this pathway is associated with executive functions, right? Next slide, the limbic loop. Well, we know a lot about the limbic with emotions, right? So that helps us remember that this is going to play a major role in socially appropriate behavior, right? So, acting, socially acceptable. Right? And you can see damage can lead to these things, right? So I would note emotional lability, which is, rapid changes in your emotions, these types of things. So if you note what's in this slide, basically that should be suffice. Do not note the pathway. I feel like you're just going to be, too much time worrying about this. And then this is definitely extremely low yield. Okay, here we have some of the states. Let me see, circles. So a lot of this makes sense, right? So when you have low levels of dopamine, bradykinesia makes sense, right? Because low levels of dopamine activates indirect pathway that inhibits movement. High dopamine, motor impulsivity, right? Lots of dopamine, direct pathway. Associate loop, this is our executive functions, right? Our associate loop is our executive functions, and we're thinking, okay, what's going to happen when we have low levels of dopamine? Well, typically this is used for executive functions. So if you don't have that level of dopamine that's required for that executive function, we'll have empty brain, which is like absence of ideas, apathy, right? The things that are opposite of actual executive functions. And if you have too much dopamine, it can lead to, impulsivity, right? flight of ideas, right? Extreme hyperactive states, right? Which is, way past the executive functions that we want, right? And lastly, we have our limbic loop, right? This is, socially acceptable behavior, right? So if you have too little dopamine, it can lead to depression, which makes sense, right? And high levels of dopamine leads to like mania and manic, right? So very like impulsive things, right? That's what I would note. That should be suffice in regards to this slide. So Huntington's disease, Huntington's disease is very interesting. It's actually I wouldn't say the opposite, but it's kind of like the opposite of Parkinson's disease in regards to the fact that it's a hyperkinetic disorder, right? Parkinson's is hypokinetic, right? Because remember, we destroyed those neurons in the substantia nigra pars compacta, and thus leading to that indirect pathway. Huntington's disease is actually the striatum is dying. So Huntington's disease, the striatum is actually dying, and it actually leads to this chorea, right? Chorea and athetosis. So as long as you know it's chorea, which is like, it's kind of like irregular, rapid, jerky movements, and athetosis are associated with Huntington's disease. Those are the two main symptoms you really want to hone in regards to Huntington's disease. So what is it? It's typically genetic, autosomal dominant, right? So basically, we have these CAG repeats, and what's interesting is that typically most people have between 6 and 35, but people with Huntington's disease have between 40 and 100, right? So they have way more, and what's interesting is that the more repeats or CAG repeats that an individual has, the worse prognosis their Huntington's disease is, right? So they know that this Huntington gene is associated with, of course, Huntington's disease. Right, so they tried understanding disease, right? They tried knockout mice, right? But what they realized is that individual mice that that they did without the Huntington gene were not able to survive, right? So we know that the Huntington gene is important for survival, so we can't just knock it out basically to treat or cure Huntington's disease, right? So it's not very well understood, but what they do know is that if you try to knock this gene out, you won't be able to survive. Right, so that's Huntington's disease. And again, you can see over here, look at the left side of this picture, right? The striatum is basically gone, right? Entire striatum basically is gone. You can see the MS projection neurons degenerate, right? The striatum is almost entirely gone, right? Here's our putamen and our cardia, and you can see it's just completely degenerated in Huntington's. So again, Parkinson's, it's those dopaminergic neurons in the substantia nigra pars compacta that are dying. In Huntington's, it's that striatum basically that's going to be affected, right? So again, you can see over here, it's a hyperkinetic disorder because what's happening in Huntington's disease is, again, remember, we still have high levels of dopamine, right? Over here from the substantia nigra pars compacta, and it's activating only the D1 pathway, right? And that's going to lead to activation of movement, and thus calling it a hyperkinetic disorder. Okay, and then the last thing I would note is that tetrabenazine it's approved to treat Huntington's disease, chorea, and that is what I would note from this slide. That's it. Okay, any questions? I know that's a little long, right? But again, it's going to take a little bit for us to understand this information. But again, we'll take a little break, of course, a couple-minute break, and then we'll get back to it with the cerebellum.
Send me your location, let's focus on communicating, cause I just need the time and place to come through. Send me your location, let's ride the vibrations. I don't need nothing else but you. At times I wonder why I fool with you, but this is new to me. This is new to you. Initially, I didn't wanna fall, but you gathered my attention. It was all for you. So don't take advantage. Don't leave my heart damaged. I understand that things go a little bit better when you plan it. Oh, so won't you send me your location? Let's focus on communicating, 'cause I just need the time and place to come through. Send me your location, let's ride the vibrations. I don't need nothing else but you. I don't wanna fall in love off of some sweet, so let's keep personal. I got a lot of cool spots that we can go. Tell me what's the move and I got you. I'm only acting like this 'cause I like you. Just give me the vibe to slide in. Oh, I might make you mine by the night. Then share me your location. Let's focus on communicating, 'cause I just need the time and place to come through. Send me your location. Let's find the vibrations. I don't need nothing else but you. Ride, 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 come and vibe with me tonight. I don't need nothing else but you. I don't need nothing else but you. Ride, 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 come and vibe with me tonight. I don't need nothing else but you. Nothing else but you. Oh, I don't need nothing else but you.
No quiero que más nadie me hable de amor, ya me cansé, de esos trucos ya me los sé, esos dolores los pasé, yeah, yeah, yeah. No quiero que más nadie me hable de amor, ya me cansé, de esos trucos ya me los sé, esos dolores los pasé. Que te odio no es secreto, ante todo lo confieso. Si pudiera te pidiera que devuelva todos los besos que te di, las palabras y todo el tiempo que perdí. Me arrepiento.
Okay. Cool. So I hope you guys enjoyed the vibes. Does anybody have any questions before we get back into the material? Okay. All right. So this is the cerebellum. Okay, cool. All right. So petition to yes, okay, I got you. Yes, I was gonna change it to Safaera, but I didn't. I forgot. But next time I will. Yes, I will definitely change it because the second lecture definitely needs a boost. You're right. I got you. All right, so we got the cerebellum, right? So here, cerebellum is really, really interesting, right? It's complicated too, but it's super interesting. So I hope you find the lecture, enjoyable and fun to understand. But again, it is going to be complex. So let me know if you want me to slow down or anything like that. But yeah, so we'll be going through the cerebellum. Okay. One thing I'll note, I forgot to put the objective slide on this as well. So if I would also recommend putting that objective slide on here. So if I forgot to upload that, but again, I would put that from his lecture on here as well as the first slide. So if you do have time, I would recommend doing that as well in order to look over that. It has some pretty good stuff on there. Okay, so we have basically the cerebellum, and the first thing we have to think about is what is the first of all, where is the cerebellum and what is its purpose, right? So those are two different things. The cerebellum is located, you can see here, right? It's on the inferior portion of the occipital lobe, right? And you can see it right here in a sagittal cut, right? And what the cerebellum is for is that not only it's important for balance, coordination, et cetera, right? It's also really, really important for neural sharpening, right? And we'll talk about that. And again, it's really important for neural sharpening. It's important for, calculating. So for example, the cortex sends signals down, says, I want to make this movement, goes through the basal ganglia, which we talked about, comes down, sends a signal to the cerebellum. Cerebellum's like, making signals, exciting, inhibiting. And basically what it does is that the cerebellum calculates the perfect, pristine movement and sends it back to the cerebellum or to the cerebrum to allow for actual conduction of the movement, right? So what it does is that it perfects that movement so that we don't overshoot and we don't undershoot, right? So that's what the cerebellum is really, really important for. So you'll see, here's a little preview. Obviously, it's not going to make too much sense now, but it will at the end. Is that Purkinje cells of the cerebellar cortex inhibit the excitatory neurons of the deep cerebellar nuclei. It obviously sounds a little foreign right now, but again, it'll make a lot more sense when we get into the lecture. But again, so we have our cerebellum, right? That's under our occipital lobe, and it basically has a cerebellar cortex, which is surrounding basically the cerebellum, and that contains some of the cells like the Purkinje cells. Right, so that's just a little overview, but it'll make a lot more sense when we go through the lecture. Okay, so first things first, where is the cerebellum? It is right here under the occipital lobe. Here's a sagittal cut. So here are the different, lobes of the cerebellum. Right, so we have the anterior lobe, we have the posterior lobe, and we have this flocculonodular lobe. Right, so here are the three different lobes. Right, so if I was to basically fold this outwards, right? So you can see if I was to flatten this, right? So this would be on the top right here, then the green portion and then the blue. This is what the structure would look like on the next image. Right, it's exactly what we just did. So this is what it looks like, right? So if I was to flatten out those lobes, right? You would see the anterior lobe right here. Here's the posterior, and this would be the flocculonodular lobe. Right, and what's interesting, about the cerebellum is the cerebellum is divided into specific parts that do different functions. So what I mean by that is that we have the vermis right here. The vermis is basically that middle portion of the cerebellum, right? And that's very, very important for conducting movement. When we talk about the deep cerebellar nuclei and stuff like that, the vermis is actually contained within the spinal cerebellum. So this right here, this dotted line, to this dotted line, in between here is the spinal cerebellum. It's called the spinal cerebellum because it sends signals to the spine, and it's important for movement, for extremity movements, trunk movements, etc. So this region of the cerebellum is solely responsible for those types of movements, right? So that's going to be that. We also have this portion right here, right? These portions outside of the dotted lines. It's called the cerebrocerebellum. Cerebral, right? Which, if we just define what it is, we know that that's going to basically send signals from the cerebellum to the cerebrum or to the, to the brain, right? And basically what it does is sends the most calculated movement you can ever think of and sends it to the brain and says, this is what we are going to send out to the rest of the body, right? So that's the cerebrocerebellum. So again, here, this is the spinal cerebellum. important for movement, right? So just movement of extremities, the trunk, etc. It contains the vermis. Outside of these dotted lines, we have the cerebral cerebellum, which is important for sending signals to the brain, a calculated signal. And then we have our floccular nodular lobe, which is this portion right here. It's the most primitive node, the most primitive lobe, and it's actually associated with the vestibular system. So it's actually called the vestibulocerebellum, right? It actually has a connection to the ear, right? It's kind of crazy, basically, but the inner ear basically connects this, not directly, but indirectly to the floccular nodular lobe, which is important for balance, right? Remember when we said balance and equilibrium? That's why it's called the vestibulocerebellum, right? So you can see here, again, quick recap, you can see this region right here within the dotted line, spinal cerebellum, right? It contains the vermis. This is very, very important in, movements of the body, extremities, as well as the trunk. Outside these dotted lines, we have our cerebrocerebellum, which is important for sending the most calculated signal to the cerebrum to say, hey, we are going to initiate this movement. And then we got the floccular nodular lobe, which is going to also be called the vestibulocerebellum, which actually has an indirect connection to the inner ear and is important for balance, right? Balance and equilibrium. Right? There's also a somatotaphic map in the spinal cerebellum. Very interesting, right? Remember what I said, right? The spinal cerebellum helps you, move your arms, move your trunks. And it makes sense why the homunculus, or the somatotaphic map looks like this. Right? This region is the vermis, right? And it's important for, the trunk movements, right? So you can see it's important for the trunk movements and some of the head. And this is the paravermal region, which is actually important for, extremity movements. But again, I think it's a little too in depth. What you just need to know is basically spinal cerebellum, important for movement, right? Extremities and trunk, and the vermis is within the spinal cerebellum. Okay. So
a little bit of a difficult time understanding. So the spinocerebellum, like, how does that, I guess, differ from the movements that the posterior or like the outside lobe is doing? Not.
How does that differ from the cerebrocerebellum?
Yeah. I don't understand like what it means by like the fine movements versus, I guess, like, is it just not fine movements?
So the spinal cerebellum, you have a bunch of pathways that connect to your spinal cerebellum that send signals out to say, okay, down the spinal column, to send it to say, okay, we're moving the arm this way or moving the leg that way. The cerebrocerebellum is highly associated with sending a signal back to your brain saying, we need to adjust this movement by this much, basically, in order to, not overshoot our arm or not undershoot our arm. Does that make sense?
Yeah, so I guess it's the spino is just doing the basic movement, and then the cerebrocerebellum is doing, like, I guess, a feedback mechanism.
Yes, exactly. Yes, exactly.
Thanks.
Yeah. So, and then we have our, floccular nodular, which is for vestibular. Okay. So now that we kind of get that, right? So here, basically, this is basically showing the deep cerebellar nuclei. So again, if I was to grab the cerebellum, right? If you have a cerebellum in your hand, right? That outside portion of the cerebellum, that's called the cerebellar cortex, right? So cerebellar cortex, right? Between the cerebellar cortex and the deep cerebellar nuclei is a bunch of white matter. So basically, again, just picture yourself holding a cerebellum. That outside portion is that cerebellar nucleus, cerebellar cortex, which contains a lot of, cell bodies, etc. So it's gray matter. And between that cerebellar cortex and the deep portion of the cerebellum, so if you were to go inside the cerebellum, like into basically the dead center, super inside, that's where the deep cerebellar nuclei are. So between the deep cerebellar nuclei and this outside portion of the cerebellar cortex, all you have is axons, right? White matter, because those are going to be the connections between the deep cerebellar nuclei and the cell bodies in the cerebellar cortex, right? So if we have that in our mind, right, we should be able to understand this image right here. Here's basically our deep cerebellar nuclei. So again, so from lateral to medial, you can see the dentate nucleus, interposed nuclei, as well as the fastigial nuclei, right? So these are going to be located, remember, deep inside of our cerebellum, super deep inside, right? That's why they're called deep cerebellar nuclei. right? And a fun way I like to remember them is don't eat greasy food, right? So you'll see on the next slide. So don't eat greasy food. That helps you remember the deep cerebellar nuclei. So going from lateral to medial, you have don't for dentate nucleus. You have E and G for emboliform and globose. So the emboliform nucleus and the globose nucleus make up the interposed nuclei. Right. So again, the interposed nuclei are made up of two nuclei, which is emboliform and globose, and then you have the F for fastigial. So you can see basically in this image, right? So again, recap. I know this is a lot. So you have your cerebellum, right? It's under your occipital lobe. Okay, you have your, if you were to grab the cerebellum, that outside portion of the cerebellum is the cerebellar cortex, right? From that outside portion to the dead center, which is the deep cerebellar nuclei, in between there, we have axons basically connecting those two cell bodies, right? Or those cell bodies. In those deep cerebellar nuclei, we have basically, 3 different types, or technically, if you were to divide it, it would be 4 of deep cerebellar nuclei. Those deep cerebellar nuclei are don't eat greasy food. So, it's going to be dentate nucleus, most lateral, then emboliform and globose, which make up the interposed nuclei, and then fastigial nucleus, right? So that's basically our deep cerebellar nuclei. And again, remember, our cerebellum is going to be divided into the spinal cerebellum, which is the middle, sends signals to the spinal cord, cerebral cerebellum, which is on the lateral hemispheres, which is going to be important for sending signals to the brain, in our basically floccular nodular lobe, which is our vestibular cerebellum, which the inner ear actually is very important for. Okay, so we got those down packed, right? Okay, and this is just basically different cuts. So we have our superior, which is in blue, our middle, which is in yellow, and our green, which is going to be our inferior cerebellar peduncle. And what these peduncles are is that these peduncles are basically connections of the cerebellum to the brainstem, right? So basically, there are a bunch of axons that connect the cerebellum to the brainstem so that we can, send our signals in or out of the cerebellum. We'll talk about each of the peduncles individually, right? But just note, look how big the middle cerebellar peduncle is. Would he put any pictures? No, I don't think he would. I don't remember there being any pictures on the neuro exam, any neuro exam. But so here's the middle cerebellar peduncle. So what I would note is that, the middle cerebellar peduncle, it's the largest. Look how large this thing is. It's actually ginormous if you actually saw it in like gross lab. So this thing is huge. And I'll talk about its importance later on. Okay. All right, cool. So again, we have our cerebellum. So here are some of the tracks, right? So we have our dorsal spinal cerebellar tract, right? So backside of the spinal cord to the cerebellum. That's why it's called dorsal spinal cerebellar tract, right? And this is going to be important, like we said, for basically movement, right? Movement of the muscles, right? So it's going to be movement of the muscles right here, this dorsal spinal cerebellar tract. And this is going to go uncrossed. It's going to stay ipsilateral to the cerebellum, right? So it goes up basically and goes straight into the cerebellum on the same side. So again, this is your cuneo-cerebellar tract right here doing the same thing. One thing I would note right here is that you have your ventral spinal cerebellar tract, right? So ventral, so means it's on the front side. This is actually going to be very important, obviously, for movements as well, but it's going to cross twice. And when it does, basically, it crosses right when it gets in from the spinal cord, it crosses, it goes up the spinal cord all the way into the cerebellum and crosses again, which is important because typically with the cerebellum, almost everything is ipsilateral, which is like, different than most structures, right? Most things in the brain are going to be contralateral, right? The cerebellum is not like that. Almost everything in the cerebellum is going to be ipsilateral in the movement that it does, right? So you can see when people have cerebellar disorders, they're typically going to have ataxia on the same side of where their disorder is, right? Because the cerebellum is typically mostly going to be ipsilateral. Right, so here's our dorsal spinal column cerebellum, which goes uncrossed, and our ventral, which actually crosses twice and goes into the superior cerebellar peduncle. Okay. So again, so I know it's a lot, but again, so just a quick recap. We have so here it is to hammer this home basically is again, the cerebellar cortex divided into 3 different areas. We have our spinal cerebellum, our cerebral cerebellum, which is, outside of these dotted lines, our spinal cerebellum, which is between the 2 lines, and our vestibular cerebellum, which is this yellow, right? So again, that's going to be all the structures, right? So we're thinking, okay, what does the cerebral cerebellum do? Okay, sends a signal via the dentate nucleus into the premotor cortex for motor planning and motor cortex. So again, the cerebral cerebellum sends a signal, and it's very important for, planning movement, right? So planning that movement, right? So again, it uses that dentate nucleus. So the way I like to think about it is like, okay, cerebral cerebellum, dentate nucleus. So what do I need to do? So D for dentate, what do I need to do? So that helps me know that the dentate nucleus is important for motor planning. What do I need to do? Right, and this makes sense because again, remember that the mnemonic we said, don't eat greasy food, right? So again, that's our don't eat greasy food. So the dentate nucleus is important for the cerebral cerebellum, right? So cerebral cerebellum, and it sends the signal to the motor cortex and important for motor planning. We have our spinal cerebellum, which has our interposed and fastigial nuclei. Right, interposed contain the globose as well as the emboliform, and then you have your fastigial nuclei, and this is for motor execution. Right, so actually executing the movement, like we said, right? So the actual execution of me moving my arms, me moving my legs, etc. Right, and again, if we go by our don't eat greasy food, that makes sense, right? Because the don't is dentate nucleus that's in the lateral hemispheres, which is the cerebral cerebellum. The eat greasy food right here, interposed and fastigial nuclei, are going to be in the spinal cerebellum. So, and they're going to be important for motor execution. And then lastly, we have our vestibular cerebellum going into our vestibular nuclei. What's important is that our vestibular nuclei is not a deep cerebellar nuclei, but your vestibular nuclei are not located in your cerebellum. They're actually located in your brainstem, right? So it's located in your brainstem, and it sends a signal basically down, and eventually it's going to, help with balance and coordination. Okay, so I know that was a lot, right? Again, cerebellum is quite complex, I understand what it does. But again, quick recap, right? So we have our cerebellum, basically, inferior to the occipital lobe. You have if you grab the cerebellum, you have your cerebellar cortex. If you go deep inside your cerebellum, you have your deep cerebellar nuclei. So again, your cerebellar cortex is divided into 3 regions: spinal cerebellum, cerebral cerebellum, and vestibular cerebellum. Right? Cerebral cerebellum, important for motor planning. Spinal cerebellum, we know motor execution. And then vestibular cerebellum, which goes to the vestibular nuclei, important for balance and coordination. Okay. So the ventral spinal cerebellar tract originates from the blank side of the body and ends at the blank side of the cerebellum once it arrives through the superior cerebellar peduncle. I'll give you a few more seconds. Okay, so the ventral spinal cerebellar tract, or VSCT, right, originates from the ipsilateral side of the body and ends at the ipsilateral side of the cerebellum, right? But remember that the VSCT crosses twice right? So it comes, let's just say from the, let's just say your right leg, it comes in, right? Stays on the right side. No, excuse me. Comes in from the right leg, crosses over, comes up, crosses back over to the right side, right? So technically it's still, comes from the ipsilateral side and stays on the ipsilateral side, even though it crosses twice, right? So this again tells us, that the cerebellum is important for, ipsilateral functions, right? Regardless of how it gets there, but it's going to be for ipsilateral functions, right? So I'm just holding that in basically for us to understand what the cerebellum typically does. Okay, so basically the best way I found basically understanding the cerebellum is dividing them by their peduncles, right? So again, quick recap, cerebellum, you grab it, you have your cerebellar cortex. Cerebellar cortex is divided into spinal cerebellum and cerebral cerebellum and vestibular cerebellum. Remember, your cerebral cerebellum has that dentate nucleus, right? In order for what do I do, that motor planning, right? Then you have your spinal cerebellum. Remember, that's important for the interposed nuclei in that fastigial nuclei, which are going to be important for, motor execution. And then vestibular cerebellum, which is important for balance and coordination, right? So that's going to be those structures. And again, so we have our superior cerebellar peduncles, right? So again, here, what these are basically going to be a bunch of axons, basically thick axons that go into and out of the cerebellum. And they just gave them a name. They called them cerebellar peduncles. So you have a superior, middle, and inferior. Right, so you can see here superior in purple, middle in yellow, and then the green is going to be the inferior. So the first one I actually like to talk about is going to be the middle, because it's really easy to understand the middle. The other ones are a little more complicated. So we're actually going to start off with talking about the middle cerebellar peduncle first. Reason being is because it's solely afferent, right? And look how large this thing is. So I'll show you on the next slide. It's actually really cool. So we have our middle cerebellar peduncle. It's ginormous. It's the largest one. And what it is that it's solely an afferent pathway. So remember, afferent means sensory information coming to the cerebellum, right? And it actually is mostly just going to be one single pathway, this pathway indicated below. So basically, the frontal cortex, you have your parietal cortex saying, okay, I want to make, this type of movement, right? Okay, so this frontal cortex sends a signal to the pontine nuclei. Pontine nuclei cross over to the other side and go into the deep cerebellar nuclei of the opposite side, right? And that's via the middle cerebellar peduncle. And what it is that these pontine nuclei are so big. Like I'm talking like these axons are ginormous. Like these pontine nuclei axons literally make up this entire middle cerebellar peduncle. It's huge. So basically, this middle cerebellar peduncle is literally made up of the axons of these pontine nuclei. So you can see right here, let's say, okay, I'm thinking, I want to make a movement, right? So, okay, frontal cortex, parietal cortex sends a signal down to these pontine nuclei located in the pons, right? And this comes into the middle cerebellar peduncle, right? Middle cerebellar peduncle. And these axons, basically, of the pontine nuclei make that middle cerebellar peduncle, right? And send it to the deep cerebellar nuclei. Okay, right? So again, solely afferent pontine nuclei cross over and go into that middle cerebellar peduncle. Okay, and that's what this is going to be important for, right? Just afferent signals sending it down, and eventually the cerebellum modifies it. And we'll show you basically, I'll show you the pathways of how the cerebellum modifies signals. Okay, so that's the middle cerebellar peduncle. Again, just think, pontine nuclei, ginormous, make up these afferent axons. Okay, so we have our inferior cerebellar peduncle. These are a little bit different. So inferior is mostly afferent, but does have some efferent, right? So again, here's an example of an afferent pathway. So I'm thinking, okay, I want to move my right arm this far to grab my cup of coffee, right? So, sends a signal down to this red nucleus. Red nucleus sends a signal down to the inferior olive. Inferior olive sends a signal to the deep cerebellar nuclei via the inferior cerebellar peduncle, right? So the way I like to remember is that the inferior olive, so as inferior, goes through the inferior cerebellar peduncle, right? So again, you can see here, here's your, okay, I want to go grab this cup of coffee, right? I want to grab it. How do I calculate that movement perfectly, right? So what happens is that, the frontal cortex sends a signal down to the red nucleus. Red nucleus comes down to the inferior olivary nucleus, goes through the inferior cerebellar peduncle and into the, let's just say, dentate nucleus. Remember, that's our deep cerebellar nuclei, which makes sense, right? This is basically telling me I want to make this movement. Cerebellum, help me out. How do I calculate this perfectly, right? I kind of have a plan. Like, I think I know what I need to do, but I need your help in order to completely, be perfect with this movement, right? And this is the pathway, one of the pathways it takes, right? And what's really interesting about the inferior olive pathway is that this pathway is extremely sensitive. Like, I'm talking like super sensitive. And the reason why is that the inferior olive actually sends climbing fibers, these things called climbing fibers, to the deep cerebellar nuclei. I know that sounds foreign right now, but I'll talk about the climbing fibers. And what they do is that they synapse with these cells, basically, certain types of cells, one-to-one, and they basically directly activate them. So the climbing fibers are extremely sensitive, right? So this pathway is very, very prominent, right? So that's what's interesting about this inferior olive pathway, is that it's extremely sensitive to changes and movements, right? This pathway is super interesting via the inferior olive, right? So that's one of the pathways. And we'll talk about, again, why that's really important as well in the feedback mechanism. I won't talk about that in this slide, but I will on the upcoming slides. But again, so quick recap, middle cerebellar peduncle, right? That's the last slide. Remember, that's solely afferent, right? Those ginormous peduncles are made up of that pontine nuclei, right? Those pontine nuclei cross over and they make up those cerebellar peduncles, right? And eventually send to the deep cerebellar nuclei. That's the middle, check, we got that. Solely afferent pontine nuclei to deep cerebellar nuclei. All right, we got that. Inferior cerebellar peduncle, here's an example of an afferent pathway, right? So I want to reach this cup of coffee, right? I want to grab this cup of coffee. How do I calculate that movement perfectly, right? So I send it down to the red nucleus. Red nucleus sends it down to the inferior olive. Inferior olive is extremely sensitive via its fibers. So those climbing fibers come in, and don't worry if you don't know what that means, I'm going to explain it later, come into the deep cerebellar nuclei, and they basically modify the signal, right? They modify the signal, right? So that's one of those pathways. This one's very important in regards to, how sensitive that is. Okay. Here's the other pathway that we just talked about. This is the same thing. Remember, we talked about the inferior olive, but again, we also have pathways from the spinal cord as well as the vestibular nuclei, which makes a lot of sense, right? So again, our vestibular nuclei is saying, okay, I want to, grab this cup of coffee, but I need to, step my foot out to keep my balance to grab it or something like that, right? That's what the vestibular nuclei in the vestibular system is important for. It's important for, containing that balance, orienting our head and eye movements in order to make sure that we're, smooth with this movement, right? So you also get signals. I think this is just insane. Like, you have like, from your ear, we talked, about the entire ear pathway, right? With that audition lecture. And again, what's really interesting is that from the inner ear, we actually have, the, vestibulocochlear nerve actually synapses on the vestibular nuclei in the pons and goes into the cerebellum. Isn't that insane? It's just like, the ear is connected to the cerebellum, right? Like indirectly, right? But it still goes to the cerebellum to help us with balance, right? Which makes sense, right? We're always saying, the inner ear is important in balance. The inner ear is important in balance and equilibrium. Right? It's connected to that cerebellum, right? Via this vestibular nuclei, right? Which comes into the cerebellum. And then we also have the spinal cord, which makes a lot of sense, just spinal cord telling us, proprioception, right? Proprioception. Remember when we talked about that? Proprioception, knowing where our arms are in body via those, those spindles. Those spindles, send a signal to the cerebellum as well. Right? So we have signals from the spindles, from the spinal cord. We have signals from the inner ear, right? We have signals from the inferior olive coming from the brain. All these signals come into the cerebellum in order to, calculate the most perfect movement in order to, execute smooth functions. Okay. And then we also have, again, inferior cerebellum, we have an efferent pathway, right? So I'm just going to talk about this one right here, again, which makes sense, cerebellar cortex going to the vestibular nuclei and then going to the rest of the body, right? This is, again, the same path that we talked about. Remember, like the inner ear connects to the vestibular nuclei and tells us, hey, we need to, put your right leg out in order to give yourself more of a base so you don't fall down if somebody pushes you, right? So that sends a signal to the cerebellum. Cerebellum, calculates it perfectly and then sends a signal out and says, okay, move your right foot out. Move your right foot out so you can maintain balance, right? So how does it do that? The cerebellar cortex sends a signal to the vestibular nuclei, and that sends it to the rest of the body, right? It tells us, hey, we need to, move our right foot out quickly in order to maintain balance. And that's exactly what's shown in this red box, right? You can see through this inferior cerebellar peduncle connected to vestibular nuclei, it tells our body, hey, you need to step your foot out in order to keep balance, right? So that's basically the inferior, that's the inferior cerebellar peduncle. So again, quick recap. I know it's a lot of information, but again, middle cerebellar peduncle, that's going to be the one that's just solely afferent, right? That's our ginormous pontine nuclei which cross over and go into the cerebellum, right? That's solely afferent. Inferior cerebellar, we have a few afferent and efferent pathways, right? I talked about the afferent pathways, right, which are going to be important. For example, the inner ear, right? Inner ear is sending a signal to the vestibular nuclei via the inferior peduncle straight into the cerebellum, and important for balance, right? And we also have an out pathway from the cerebellum out the vestibular nuclei, and to tell our body, hey, step your right foot out. You need to keep more balance with your body, right? And then lastly, we have our superior cerebellar peduncle. So these are mostly efferent, and I do have some afferent pathways, but here's an example of an efferent, right? So here's our superior cerebellar peduncle. So it's kind of like, okay, we have our cerebellar cortex, right? Remember, what's between the cerebellar cortex and the deep cerebellar nuclei? Just a bunch of axons, right, which connect to them via the superior cerebellar peduncle. We go to the thalamus, and then we go to the premotor cortex. Right, and what this is important for is basically, sending a signal back to the brain to tell us, you made a mistake, right? We need to adjust this in order to send more outputs out. It's kind of like that feedback mechanism, right? Everything about the cerebellum is feedbacking things, sharpening things, right? Neural sharpening. And then last one, again, this is the same thing we talked about on the last slide or 2 slides ago, but this is just via the superior cerebellar peduncle, which makes sense. The reason why it's easier for me to think about that is because, this right here goes to the superior colliculus, right? So superior cerebellar peduncle, reticular formation, and into the rest of the body. And what's interesting about the reticular formation is that area actually controls almost all movements of the body, right? The reticular formation is ginormous. It almost contains the entire brainstem. It's super, super important. We talk a lot about it with wakefulness and stuff like that. But the reticular formation is actually extremely important with orienting, all of your bodily movements, right? So that's actually a very important area. And that's that. Okay, so quick question before we move on. So this pathway basically, for example, frontal cortex to the red nucleus to the inferior olive. Remember, this is what takes those climbing fibers to the deep cerebellar nuclei. So which cerebellar peduncle does that go through? Again, I know it's a lot of pathways, right? So as long as you break them down into their components, like I've been trying to do, you'll be able to get them down. Okay, give you a few more seconds. Okay, so we have frontal cortex to red nucleus to inferior olive via the inferior cerebellar peduncle into the deep cerebellar nuclei, right? So again, inferior cerebellar peduncle via those climbing fibers. Those climbing fibers are really, really sensitive, which we'll talk about. And again, remember, your deep cerebellar nuclei are your don't eat greasy food. If it's not part of that don't eat greasy food, it's not deep cerebellar nuclei. Right? But again, important to note, remember, emboliform and globose together make up the interposed nuclei, right? Okay. So again, like I talked about, remember, there's a feedback mechanism in regards to all of this, right? And it's to no surprise that this feedback mechanism is via this red nucleus, inferior olive, and to the deep cerebellar nuclei / Purkinje cell, right? There's no surprise, right? Which makes sense, right? Because, for example, if I wanted to, change a movement, right? Let's just say it goes from the deep cerebellar nuclei, well, let's just say Purkinje cell, down to the deep cerebellar nuclei, to the red nucleus, to the inferior olive. Inferior olive sends climbing fibers to the deep cerebellar nuclei and the Purkinje cells. And again, this triangle, it's actually given a name. I forgot which scientist made this, but it's like, I think, 2 scientists' name. But basically, this triangle basically is a feedback mechanism that's extremely, extremely sensitive. And it basically causes modulations in movement in order to allow us to calculate, motor output, right? And it's because of these climbing fibers via this inferior olive, right? These climbing fibers. So the inferior olive are the ones that produce these climbing fibers, right? And this is that feedback mechanism, this feedback circuit, which kind of looks like a triangle, right? Okay. You can see that here too, right? Same thing. Okay, so that's everything. Any questions? I know it's a lot of information in regards to the peduncles. Hope not boring you guys. I know it's a lot of information, but again, we got to get that down somehow. Okay, cool. If you guys don't, just let me know if you have questions after. Okay, so we have cerebellar cortex. So again, remember, this is basically the outside portion of your cerebellum. Right? You have 3 different layers, right? So 3 different layers: molecular, Purkinje, and then granular, from superficial to deep. Right? So these are the 3 different layers of the cerebellar cortex. Right? And we'll talk about the certain cells and within each layer and their importance, right? And what they're important for. Okay. So you're probably thinking, what are these mossy fibers? We didn't talk too much about mossy, but what are these climbing fibers? Like, what are they? Like, I'm confused, right? Which makes, makes sense. Like, what, you never heard of these before, probably. What do they do? Okay. So the first thing you want to know is that mossy fibers are basically, those are fibers that come from, almost anything gives mossy fibers to the cerebellum, like connections from the spinal cord, send signals to the cerebellum via mossy fibers, right? Almost anything that gets into the cerebellum is via mossy fibers. The only thing that's climbing fibers is when it comes from the inferior olive. So when there's a signal, for example, from the inferior olive to the cerebellum, it's via these climbing fibers. When it's via the spinal cord, for example, it's these mossy fibers. And you're probably thinking, what is mossy fibers? That makes sense, right? Okay, set signals from the inferior olive, are climbing fibers. Everything else is mossy. But what are they, right? What do they do? Which is a valid question, right? What do they do? And I'll tell you on the next slide. So here, this is a great picture, I feel like, in regards to understanding what these fibers do. Right, so this is basically signals. For example, mossy fibers are like, okay, you moved your right arm, a little too far. I'm sending a signal back to the cerebellar cortex saying, we need to adjust this. Right? Same thing goes with the, climbing fibers. So with the climbing fibers, basically, these come from the inferior olive. And basically, this is this feedback circuit like we talked about. And what do these climbing fibers do? Right? These climbing fibers, when they come in, they say, okay, I'm going to activate the deep cerebellar nuclei, but I'm also going to activate the Purkinje cells. Right? So the purple is the Purkinje cell. Again, our 3 layers are molecular, Purkinje, and granular. And you're probably thinking, how are the climbing fibers, activating the deep cerebellar nuclei, but they're also activating the Purkinje cells? Because the deep cerebellar nuclei are excitatory, but the Purkinje cells are inhibitory. Important to know. You want to know that the Purkinje cells are inhibitory. That's very, very important, right? So, and you're thinking, why would you activate something and inhibit something that inhibits the activator, right? And you're thinking, why does it do that? That's important in the role of neural sharpening, right? That's the purpose of the cerebellum. It's to, I want to activate this cerebellar nuclei to tell me, to move my arm this way. But if I move my arm too far, I also want to activate the Purkinje cell to tell me, hey, you moved your arm too far. You need to decrease that. Right? It's all about that modulation. That's why these climbing fibers, activate the deep cerebellar nuclei as well as the Purkinje cells. And remember what I said, these climbing fibers are really, really sensitive, right? They're extremely sensitive, right? And they're going to be connected to these Purkinje cells. Again, climbing fibers to Purkinje cells from the inferior olive. Okay, so that's climbing fibers. We also have mossy fibers, right? Mossy fibers basically come from the spinal cord, for example, saying, this is what you did via proprioception. How do we change this? Right? Mossy fibers aren't as sensitive, right? Because they're not like one-to-one. But what they do is that they activate granule cells, right? And these granule cells eventually send fibers up, which we'll talk about. And what it does is like it activates these granule cells, and it also activates Golgi cells. And we're probably thinking, why would it activate the Golgi cells? But again, remember, it's important in this modulation. If I activate these granule cells too much, I want to activate these Golgi cells so that they inhibit these granule cells. Right? It's always about that, too much, too little. It's that yin and yang, right? It's kind of like that back and forth. That's why we have these fibers activating activators and activating inhibitors, right? You have that balance in these mossy fibers right here, and you have that balance in these climbing fibers right here, right? And again, something really important you want to know is, again, remember, climbing fibers, they excite the Purkinje cells, which are inhibitory, right? As well as the deep cerebellar nuclei. Mossy fibers excite the granule cells. But an important thing is that these mossy fibers come up to the cerebellar cortex and they form parallel fibers. Right? So what happens is that these fibers from the granule cells come straight up. Once they get to a superficial portion of the cerebellar cortex, they go outwards. Right? They go completely outwards, and they're called parallel fibers. Right? And these parallel fibers are going to activate these cells called stellate and basket cells. So again, he didn't talk too much about the stellate and basket cells, but to no surprise, right, these stellate and basket cells inhibit the Purkinje cells, right? So again, we have more modulation, right? We have activation, inhibition, activation, inhibition, activation, inhibition, in order to get that perfect output, so that we make sure that the signal is not too strong or not too soft or not too, too weak, right? And that's exactly what these climbing fibers and mossy fibers are. Okay. I know I went on a little rant there, but does anybody have any questions? Does that make a little bit more sense? Okay. Okay. I hope y'all are still in there. Okay, so again, so now this makes sense, right? So again, remember what we said. Climbing fibers inhibit climbing fibers excite Purkinje cells. They also excite deep cerebellar nuclei. But again, if you excite a Purkinje cell, it inhibits the deep cerebellar nuclei. So that's that modulation, right? It's that excitation, inhibition, modulation of these cerebellar nuclei, which causes an output, right? So again, that's that climbing fibers. We also have mossy fibers, which come straight up and form these parallel fibers, right? Which activate or inactivate different things. Okay. So those are going to be those roles of those fibers. So again, one thing important to know is just, the cerebellum plays a major role in anticipation responses. That's the most important thing you want to note here, right? That, before something's actually going to happen, the cerebellum plays an important role. That suffice. That should be good enough in regards to this. You don't need to worry too much about that. Okay. So cerebellar model. So here, again, remember, climbing fibers only come from the inferior olive. So inferior olive to Purkinje cells, right? Again, climbing fibers are going to do what? They are going to excite the Purkinje cells. So Purkinje cells, once they're excited, they inhibit the deep cerebellar nuclei. You also have pontine nuclei, which remember those pontine nuclei are huge, right? They come in through that middle cerebellar peduncle and basically, form afferent fibers. So, and it sends it to the Purkinje cells, and it modulates motor output. That's exactly what this does. It's all about that modulation in regards to motor output. Okay, same thing here, right? Okay, what's interesting here about long-term depression, is that in order for long-term depression to occur, right, which is like internalization of receptors, right, what has to happen is that the climbing fibers and the parallel fibers have to activate simultaneously, right? And if you remember, where were the parallel fibers from? The parallel fibers came from those, you remember, those mossy fibers, right? So the mossy fibers came up, they synapsed at the granule cells, they went up and formed those parallel fibers. Those parallel fibers and the climbing fibers have to simultaneously activate the Purkinje cell at the same time. And what happens is that when that Purkinje cell is simultaneously activated at the same time, it's going to, obviously lead to this, entire pathway, right? It leads to activation, AMPA receptors, et cetera, et cetera. But the main thing that happens is that, these AMPA receptors become internalized and leads to long-term depression, right? Long-term depression, obviously, of these receptors, right? And this is the general pathway of how it goes. Okay. Mossy fibers activate which structures directly? So which is stronger? So in regards to strength, the climbing fibers are extremely sensitive. They're very strong, right? So the climbing fibers are definitely one of the strongest ones in regards to signals of excitation. But again, the climbing fibers are affecting the Purkinje cells. So thus the inhibition from the Purkinje cells can be just as strong, right? So it just depends on the output and input of the signals. Great question, though. Okay, I'll give you a few more seconds. Okay, cool. So we have the mossy fibers activate which structures directly, and that's going to be very good job. F, the granule cells and the Golgi cells. Okay, good. So you guys are definitely, processing some of this information. I know it's a lot of info coming at once, but that's really good to know this based off just listening from this lecture. So yeah, C and D. Yep. The climbing fibers activate the Purkinje cells as well as the deep cerebellar nuclei. Okay, and then so cerebellar dysfunction. So, what is a sign of that? Nystagmus, which is just, shaking of the eye, and when the eyes shake really quickly. Dysmetria is basically if I were to, I was trying to grab a cup of coffee, my arm went too far, or my arm didn't make it. Right, that's dysmetria. Dysdiadokinesia is basically, so for example, if I was to put my hand out and said, flap your hand on your hand as fast as possible, right? Do that basically. If you can't do that, that's a sign basically of cerebellar dysfunction. But you should be able to go back and forth, flip your hand back and forth on top of your hand pretty quickly. And if you can't, that's a sign of cerebellar dysfunction. And it's really cool, right? So, and then we also have assynergia. It makes sense. A decomposition of movement, tremors, and errors of gait. So I would definitely note these, normal signs of cerebellar dysfunction, or typical. I'm not going to go over this one because it's exactly what we talked about on the last slide, right? Or last few slides. Okay, and then we have this experiment, right? So what happened here? So basically, they cut the lateral rectus of the left eye. So meaning the left eye was weak, right? It's not able to, AB duct, right? So it's weak. So what's happening is that they put a patch on the left eye. So like, okay, the left eye is weak. We put a patch. What's going to happen if we tell them to look at an object, let's say like, to the right or to the left, right? So if you tell somebody to look at an object, right, let's just say to the right, the right eye is going to be perfectly aligned with that object. So you can see it's perfectly aligned. But the left eye is not going to be able to make it. It'll actually undershoot. Reason being is because the left eye is weak, right? It doesn't, the lateral rectus isn't there, right? So it won't be able to do that. It's actually going to undershoot, right? So what they did is they're like, okay, so let's see what happens if we move the patch to the right eye, okay? So now you have a patch in your perfectly normal right eye, right? And your left eye is definitely affected because that lateral rectus muscle is not working. So what's happening is that if I was to tell you to look at something now, technically you're only using your left eye. Your left eye is not going to get there at first, but eventually after practice, it'll eventually be able to get to that position. But what's going to happen to the right eye? The right eye is going to way overshoot, right? Because think about it, your right eye is normal, right? It's seeing perfectly, but because it has a patch on it, it's not going to be able to, to perfectly align with where the object is. So it's going to use the left eye as a basis, which is why the right eye completely overshoots as the left eye is trying to get normal. And then the same thing 5 days after, the right eye is still way overshooting as the left eye finally gets in line, right? So again, that just shows you basically the differences basically in regards to how the eyes can adjust in regards to when one is covered over the other. And then lastly, we have this vestibulo-ocular reflex, which is actually really, really cool. What this is that, so if you were to stick your thumb out, right? So if you stick your thumb out right now and you just look at it, right? Just look at your thumb. If you move your head side to side, but keep your eyes fixed at your thumb, right? So keep your eyes fixed at your thumb and you move your head side to side, right? Try to keep the thumb as focused as possible. So see if the thumb will ever turn blurry. So just go back and forth and just look at your thumb. Did your thumb like go blurry? No, right? You're pretty focused on your thumb, right? No matter how fast your head can move, right? So you're pretty good at orienting where your thumb is. So now, if you keep your head still, don't move your head, but you move your thumb side to side and try and keep it focused. Try not to make the image blurry. Let's see what happens. So you remember, keep your head straight and try to move your thumb side to side and try to keep it in focus. Super blurry, right? Like I can't even focus on my thumb, right? Super, super blurry, right? And that's what this is basically. So this is we have this thing. So because it's super blurry, I'll explain why that makes sense. So the reason why we can see our thumb, for example, and go back and forth like this, right, and not move our thumb and still be clear, it's because we have a vestibulo-ocular reflex. So a reflex from the ear, right, to the right, obviously from the ear basically to the vestibular system, yeah, right? And basically it's important for us, in orienting head and eye movement. Because remember, we always talk about, the inner ear, the colliculi, they're very important in orienting head and eye movement, right? And it's very, very fast, right? It's super fast, actually. It has ion channels that are just extremely fast, which is why we can still focus on our thumb no matter how fast we move our head, right? But if we move our thumb, right, and don't move our head, it becomes blurry very quickly, right? So that's because that's dependent on the visual system, and the visual system is extremely slow. We have 10 layers in the retina, lots of GPCRs, extremely slow, so things get out of focus super fast, right? So that's how we know we have a vestibulo-ocular and we don't have, like a vestibular visual, right? We don't have a vestibular visual reflex, right? And that's exactly what they're testing here, right? So basically, they did minifying glasses, and what happened here is that minifying glasses actually leads to people looking half the size, right? So you can see this individual right here is half the size, right, via those glasses. And what's happening is that, the person's still in the same spot. So you said your head doesn't need to move as far, but your eyes need to move more to the right, right? Because the person is half the size, right? So instead of just looking straight ahead, now your eyes have to look to the right, right? For example, they have to look to the right. So this is basically how you can see that your head movement is not going to align with your eye movements with minifying glasses. But eventually, after a very long time, after practice and practice, your eyes will be able to align perfectly with your head. And that's basically what this experiment does. It tested out basically that vestibulo-ocular reflex. Lastly, we have cerebellar lesions. So again, the cerebellum is not just movement. It can lead to cognitive dysfunctions, right? So this is why it's called cerebellar cognitive affective syndrome, as well as dysmetria of thought. But again, it's just not about only motor issues. It can lead to cognitive dysfunctions as well. That's it. Okay. Any questions? I hope you guys enjoyed that. I know it was a lot, but Does anybody have any questions before I let y'all go?